Hello, I am Byungmin Kim from Triple IXR Lab at Korea University. Today, I will present our paper titled Shaping the Future of VR Hand Interactions Lessons Learned from Modern Methods. In virtual reality, using an avatar's hands to manipulate virtual objects is crucial for intuitive control and immersion. However, hardware limitations often prevent perfect representation of hand movements, so researchers have proposed various approximation-based approaches. Despite these developments, there has been little direct comparison among different methods, which makes it difficult for developers to choose the most suitable approach or to verify whether newer technologies truly improve the user experience. To address this, we implemented three state-of-the-art hand-object interaction models that differ in terms of visual plausibility and physical plausibility, and then we conducted user studies. Our first goal was to analyze and compare each model's strengths and weaknesses through two experiments. Based on these findings, we derived design guidelines and suggestions for future development. Before I explain the experiments, let me briefly describe the three methods we compared. The first method is called the attachment with controller method. This method uses colliders for collision detection to align an object surface with the hand surface, which leads to relatively low visual and physical mapping performance. In this approach, the hand has finger colliders and a palm colliders placed at each joint. The user first brings the palm close to the object. Once the palm collider collides with the object, the user presses a button on the controller to gradually bend the fingers. When the fingers reach the object, they stop bending and the object is attached to the palm when the grasping is stable. Although this is simple and fast, it supports only two states, attached or not, so force control is not possible. The second method is called the penetration with tracking method. This approach uses the VR headset's built-in hand tracking. Because the rear hand inevitably penetrates the virtual object, this method uses the degree of penetration to control the amount of force applied, allowing for moderate physical mapping. At the same time, inverse kinematics is used to provide high visual mapping. In this method, there is a rendered hand that visually displays the hand shape and a tracked hand that is actually being tracked by the device. When the rendered hand contacts the object, it stops at the contact point, while the tracked hand penetrates the object. The penetration depth, measured from the initial contact point, determines the force exerted by the fingers. In other words, deeper penetration means a stronger grip, which allows for detailed force control. The third method is the torque-driven with controller method. It learns each joint's torque by using a handcrafted dataset and reinforcement learning. Because the fingers' bending forces are trained on actual human data, it achieves the highest physical mapping, while its visual mapping is low and based on collisions between the hand and the object. Reinforcement learning model uses the handcrafted dataset to learn the torque for each joint. We use the pre-trained hand agent from a paper. Since how much you press the controller button influences the torque, this method allows for very precise force control. To evaluate these three methods, we designed two experiments. The first experiment is the object relocation task, which checks whether user can perform stable fundamental interactions with objects. In this task, three panels labeled RGB are randomly generated among 9 locations on a table, and one object appears in front of the user. the user must first grip the object securely, then rotate it to find the sections labeled R, G, B. After identifying one of those letters, the user places that labeled site on the matched colored panel. If the user succeeds, a new object appears. The second experiment is the tower building task, which focuses on object-object interaction and requires finer control than object relocation task. In this task, multiple objects are placed on a table. The user stacks them one atop another and must keep them balanced. To confirm that the object tower is properly built, it must remain stable for 5 seconds before moving on the next stage. If the user's hand touches the object and if any object falls during this time, the timer resets to 0. As you can see in the video, the progress bar indicating the stability time resets whenever the hand touches the objects or when an object falls. If an object falls, the user must rebuild the tower before proceeding. After successfully keeping the tower stable for 5 seconds, one more object is added, and this process repeats. We conducted the user study with 24 participants. Each participant performed both tasks with all 3 methods and provided ratings on usability, workload, immersion, and naturalness, followed by a brief interview. From these interviews, we summarized the frequently mentioned pros and cons for each method. Participants noted that the attachment with controller method was easy to use and showed overall top performance. However, they mentioned difficulty in picking up small objects and noted that the object sometimes stayed attached even when the hand pose shouldn't have been able to hold it. This mismatch, where the object appears to be held despite the hand not being in a proper gripping shape, seemed to reduce the sense of realism for users. We concluded that better grasping logic for attaching is needed to prevent it. Next, participants felt that the penetration with tracking method produces the most natural hand shapes and had high potential thanks to real hand tracking. But they found objects somewhat unstable because force equilibrium was not considered, and they also complained of high workload from having to keep mimicking the grabbing motion in midair. We believe that integrating force equilibrium could provide more stability and reduce the workload. Finally, participants said the torque driven with controller method was the best at handling complex objects thanks to torque learned directly from human data, and they liked the precise force control achieved through pressing the controller button. On the other hand, they had trouble picking up small objects, and some felt the distal joints of the index and middle fingers were not fully utilized. Therefore, we suggested to improve the training process potentially by weighting those critical fingers more heavily during the data-driven reinforcement learning stage. By comparing these 3 methods, we were able to propose practical guidelines for the development of VR hand-object interaction systems. We hope our study will offer valuable insights to researchers and developers looking to create more intuitive and realistic hand interaction in virtual environments. Thank you for listening to my presentation.